talk about the energy transport in stellar interiors. Now, you see, the energy that a star radiates from its surface is generally replenished from sources, right? So, whatever we see, a star radiates, basically, this is replenished by the energy created from the source inside the sun, which is the fusion in the core, or basically reservoir located in its hot central region, right? Now, this represents an outward energy flux, you see, high to low, outward energy flux at every layer in the star, and it requires an effective means of what? Means of transporting energy through the stellar material. Now, this transport of energy is possible owing to non-zero temperature gradient in the star, and we have talked about the temperature gradient during our discussion on local thermodynamic equilibrium. Now, while radiation is often the most important means of energy transport and it is always present, it is not the only means, right? We can also have conduction and convection as well. You see, in the stellar interior, where matter and radiation are always in LTE and the mean free path of both photons and gas particles are extremely small, heat can be transported. So, basically, heat transport we can have by basically two very important ways. One is random thermal motion. Random thermal motion of particles, and when I say particles, I mean both photons and gas particles, and this is by a process that can be called heat diffusion. Okay, now in the case of photons, the process is known as radiative diffusion. Okay, and in the case of gas particles, it is called heat conduction. Now, the other very important way is the collective bulk motion. Bulk motion of gas particles, and this is basically, since the previous one was heat diffusion, this is basically convection. Okay. Now, this is an important process in stellar interiors, not only because it can transport energy very efficiently, but also because it results in rapid mixing. So, there is a very rapid mixing because of this. Okay. So, now let me first talk about the heat diffusion process. Okay. But before that, what we will have to remember, I have already discussed, is you must remember that we have talked about the local energy conservation principles, or basically local energy conservation. From here we get a stellar structure equation, and what was that? Basically it is the energy equation. You remember that I discussed in the first lecture, or first or second lecture. So this will come in handy during our discussion question. So what was that? So this is, let me write it down. So this is basically what we derived previously. Remember, Q minus del F del m. So this is the energy equation, and basically this tells us about the local energy conservation in stars. So let us come back to our topic of energy transport by radiation and conduction first. We will talk about radiation and conduction first. Now, so energy transport by radiation and conduction. We will talk about this first and then convection later on. So, again, let us go to observations. Well, we have seen that most stars are in a long-lived state of thermal equilibrium, right? In which the energy generation in the stellar center exactly balances the radiative loss from the surface. So, most stars, they are in thermal equilibrium. So this means that energy generation in center exactly balances the radiative loss from surface, right? Now, what would happen if the energy generation source is suddenly quenched? Well, the answer is very little will happen, at least initially. Let us see how. You see, photons that carry the energy are continually scattered, absorbed and re-emitted in random directions. Because the stellar matter is very opaque to radiation, not transparent but opaque. So, the photon mean free path is very small. Right, we have just discussed about this in our LT discussion. So, it is of the order of 1 centimeter. And what does it compare to the solar radius? Very, very small. Now, as a result, the radiation is basically trapped within the stellar interior, and photons diffuse outward very slowly by a random walk process. And next you will be wondering, so what is the time that it takes the radiation to escape from the center of the sun by this random walk process? Basically, the time required to escape using by random walk, you know how much is this? It is 10 to the power 7 years. It's such a big number. Now I will talk about this in a illustration, which maybe in the next class we will talk about this calculation through a problem. So note that this time is a very long time, even given the fact that photons travel at the speed of light. So what does this mean? This means that the changes in sun's luminosity will occur after millions of years. So even if there is some change going on in the solar center right now, we will know if we exist on Earth after several millions of years. Okay. And that is on the time scale for radiative energy transport. Right. Which is basically the Kelvin-Helmholtz time scale for thermal readjustment. Okay. Now, let me talk about again little bit about the LTE. Okay. Now, we have already estimated the temperature difference over this length scale. So, temperature difference over length scale, and this is about the length scale. Over this length scale, the temperature difference was about 10 to the power minus 4 Kelvin, and so this means that the radiation field, so this means radiation field is extremely close close to black body radiation. Right, so this is our energy density. Right. Now, black body radiation is isotropic, and as a result, no net energy transport would take place. However, a small anisotropy is still present due to tiny relative temperature difference. Remember this thing, a very tiny number, but still it is present. And this small anisotropy is enough to carry the entire energy flux in the sun. Again, this will be, I will discuss using a second example. So the first example I will talk about is the time required. Not today, next class. And this is the second example. Now, these two estimates, what do they show us? These estimates show that radiative energy transport in stellar interiors, they can be described by a diffusion process, and this yields a great simplification of the physical description. Okay, we will now talk about heat diffusion by random motions. Fine. Now you must remember the fixed law of diffusion. Anyway, let us repeat this. So what does this law tells us? It tells us that whenever there is a gradient delta n in density of particles of a certain type, then the diffusive flux J, which is basically the net flux of such particles per unit area per second, and this is given by, J is equal to minus d grad n, with d is equal to 1 by 3 V average into L. Okay, and this D is basically diffusion coefficient, which depends on the average particle velocity, which is this, and their mean free path. So this depends on average velocity and also the mean free path. Okay, now let us try to understand the origin of this equation, that is the fixed law of diffusion. Okay, now let us consider a unit surface area and particles crossing the surface in either directions. Let z be the coordinate in the direction perpendicular to the surface. Okay. Now the number of particles crossing in the positive z direction, আমি আর ছবি কিছু আঁকছি না, let me just write down the relation. Okay, so as I was saying, let me consider a unit surface area and particles crossing the surface in either direction. If z coordinate be the direction perpendicular to surface, then the number of particles crossing in positive z direction, what is it? This is basically dn dt equal to 1 by 6 n V average. Now why does this 1 by 6 occur? Well, This comes from the fact that half of the particles cross the surface in one direction, and because their motions are isotropic, the average velocity perpendicular to the surface is 1 by 3 v average. Now this can be proven in the same way as the factor 1 by 3 appearing in the pressure integral. Remember that we talked about previously? Now, if there is a gradient in the particle density along the plus z direction, so in case of a gradient in particle density in z direction, which is basically del n del z, then the particles moving upward with mean free path L on average, so mean free path L on an average, they will have a density of n into z minus L, and those moving down, so this is moving up upwards, and those moving down, what about them? They will have a density of nz plus L. So you see, there will be a net particle flux across the surface, and that is basically given by this term. Let me show this to you here. So this is the difference between the two of them. Okay. Now basically the equation that we wrote down previously, which is basically this relation, is a generalization of this relationship. Okay, so this is sort of how we prove this relation. Now suppose that in addition to the gradient in particle density, there is a gradient in energy density. So along with gradient in particle density, there is also gradient in energy density carried by these particles, which may be photons or gas particles. Then by analogy, there is a net flux of energy across the surface, since the particles moving up on average carry more energy than those moving down. And when I say moving up, I mean moving outwards. Okay, so this is moving up and this one is moving down, right? And therefore a gradient in the energy density gives rise to the net energy flux. So let me write it down. So this time the net energy flux is due to the energy density gradient, right? So this is, say, how we derive this relationship in analogy with the fixed law of diffusion applied to the particles. Okay. Now, since a gradient in energy density is associated with a temperature gradient, so we have basically del U del T constant V into grad T. So this is equal to basically CV into gradient T. Thus we can write this as an equation of heat conduction. So basically we will have, you see, this relation here. We can write like this. So let this be equation 1. where K is the conductivity. Remember that this description is valid for all particles in LTE. So this is valid for all particles in LTE. And when I say particles, I mean both gas particles and also photons. Okay. Fine. Now, for photons, let us take V average